about these vocabulary terms. So half-life, the time it takes for half of the radioactive nuclei in a given sample to undergo decay. So it doesn't matter whether you have 10, 20, or 100. In one half-life, half of it will go away. Divide by 2. Mass, measured in grams or kilograms usually when we're talking about half-life. How much stuff remains, specifically usually how much radioactive parent atom remains. And finally, radioactive decay, when an atom releases radiation and changes into a different atom. So that would be the parent changing into the daughter. So it could be carbon-14 changing into nitrogen, or it could be uranium eventually decaying to lead. I don't know, it depends on the atom. These are all the formulas you could possibly want to calculate anything to do with half-life or mass or percentage when it comes to half-life. So up top here, we have 2 different formulas for finding how much mass remains. Now, the difference between these 2 formulas is this top one is you have to know the number of half-lives that have passed to get this top formula. If you don't know the number of half-lives and instead you know the time and the half-life of the element, then you can use this bottom formula down here. They're basically the same thing except that one last change. Now, you may notice something about this formula right here. Time divided by half-lives, that's right here. The number of half-lives equals time divided by half-life. So all it is just this formula is put in here for this. So actually, you could use this upper formula and just put time divided by half-lives as well. It's really up to you which one you want to use. They're interchangeable. The time. So let's say you're given the number of half-lives that have passed, and you're given the half-life for that particular element. So number of half-lives times half-life of that element gives you how much time has passed. The last one down here is basically the same as mass. The only difference is instead of mass, we have percentage. So instead of maybe 100 grams original mass, 100% original percent. Usually when it comes to percent, you're always going to start out with 100. I haven't ran into any problems that you don't start out with 100% of the original parent material. So you can keep that in mind. If you want to change this to 100% instead of original percent, you're probably safe, at least for most questions. Everything else remains the same, and then your final answer, instead of being grams, will be percentage. That's basically it for that formula. So that's all the formulas you could possibly need. So here are some common half-lives that you might see in questions. These are also some of the more common half-lives, at least these ones up here, used for dating the age of fossils and rocks. Now let's go look at a couple of practice questions. First practice question, if a rock contains 50% impaired material, how many half-lives have passed? Percentages, when you are doing them, you always assume 100% impaired material. So 50% left would signify that 1 half-life has passed. If you only had 25% parent material left, that would be 2 half-lives. If you had 12.5, 3 half-lives have passed. So 100 divided by 2, 3 times. What if you're asked to find the age of a rock? If you know the half-life and how many half-lives have passed, you could find the age. So for example, if a rock's half-life is 25 years and 2 half-lives have passed, the rock would be 50 years old. Or if a rock's half-life is 50 years for that isotope that's inside of it, and 3 half-lives have passed, that would be a 150-year-old rock. Now, when it comes to absolute dating and isotopes, only very long half-life isotopes can be used to date really old objects. If you have something like carbon-14 with a half-life of 5,730 years, well, after about 60,000 years, or about 10 half-lives, you would only have 0.04% of that carbon-14 left. And that's not a lot. That's not a lot that you could actually measure with. So carbon-14 can't be used to date old objects, at least not anything older than 60,000 years. You would need a different isotope to date really old objects, so perhaps potassium or even uranium. Strontium can also be used as well. But what about really young objects? So you probably couldn't use uranium-238 to date a bone that was only 10 or 100 years old. Just none of the uranium would have decayed, let alone the fact that there might not even be uranium inside the bone to begin with. So you can't use really, really long half-life objects to date something that's very, very young. You would need a short half-life object like perhaps carbon-14 or something even shorter. Now, theoretically, if you were doing half-life and every half-life that passes divides the amount by 2, well, theoretically, you would never run out of parent material. It would just be less and less and less as a percentage. In actuality, there will be a point in time where most parent materials will decay into daughter atoms. So, for example, if you have a piece of wood and you have it decay and half-lives pass and millions of years go by, there will be a point in time where every last carbon atom in that sample has decayed. Here are some final questions you could look at. What is something you can't date with carbon 14? Anything that didn't used to be alive cannot be dated with carbon 14. Let's say you have 100 grams of carbon 14 and you wanted to know how many grams are left after one half-life. Just like with our percent question, you take the original amount, divided by 2 for one time, and you get 50 grams. But what if about 7 half-lives? You would need to use the formula shown earlier in the presentation. You would have 100 divided by 2 to the 7th power. What about 3.5 half-lives? You would take your original 100 grams divided by 2 to the 3.5th power. You should get an answer somewhere around somewhere around 8.8. If you did, you know how to do this. If not, check your calculator to see if you made a calculation error.